Hey everybody, doing a mic check. If you can hear me, say something in the chat, please. Thanks. Check, check, test. Hey everybody, Troy Carpenter here, coming to you live from the new Goldendale Observatory in 3D. Of course, that's not true. You're watching on a two-dimensional monitor of some sort, I'm sure. But we're going to talk about three-dimensional space tonight. We have once again terrible weather. It is foggy and raining, and we supposedly had a little snow earlier, so this is kind of becoming a trend with these shows. I would love to show you some live telescope views if I could. I cannot currently do that. But if it changes, I'll let you know. That may not be a true statement, though. I don't know if I'll get around to running over there and getting the dome open in time. So anyway, three-dimensional space is a topic that sounds simple, and it actually kind of is. There's a lot of common sense associated with this topic, but it is worth discussing. There's also some misconceptions, and primarily the misconception is just how big the universe is. People tend to think it's smaller than it is, and then when they think they have their head wrapped around the concept, it's still not adequate. The reality is the universe is vast and deep beyond most people's understanding, and we're going to hope to change that a little bit tonight. Those of you who've never been to one of these shows, this is what we're doing in the meantime while we wait to reopen, and we strongly encourage you to behave the same way you would if you were here in person, and that is asking questions and making comments. We like questions and comments. It makes the show better. It allows us to tailor the presentation to your experience, to your level of understanding. If you don't understand something tonight, let me know. If you don't know a certain word, let me know. I will define it. Speaking of words, we will be adding some, hopefully some vocabulary to your personal lexicon tonight. Some new words to think about, discuss with your friends. So, let's test it. Let's see if the chat's working. 1, 2, 3. What did I just say? Let's see how fast you guys are. 1, 2, 3. Silence. You people are slow. Type faster. We only have a 4-second latency now with our awesome YouTube Live. There we go. Thank you. Someone said it. Thank you. All right. So we have a functioning chat. All right. So the 3D universe. I'm gonna get right down to it. I'm gonna show you a cool video, and we'll hopefully hopefully inspire a few questions. Check this out. What's that? That is a famous shape. Let's see if you can identify it. Anyone know what that shape is? Come on, what's that shape? Type. Say things. Really? There, okay, a dipper. Oh, even better. Someone was very specific and said Ursa Major. It is true that the Big Dipper is part of Ursa Major. Ursa Major is a constellation. However, the Big Dipper is what we call an asterism. It's a shape within a constellation, an unofficial shape. Well, watch this. I'm gonna, oh, what's happening? What's going on? I just paused it. Did I just spin the constellation? Not really. I changed our vantage point. Constellations are a figment of your perspective. They only appear the way they do because of where you are. Because of all those stars being at different depths, if you were to somehow move across the cosmos, living on another planet perhaps, orbiting another star, the constellations that you take for granted here on Earth would be unrecognizable. The Big Dipper, this shape, totally alters itself depending on where you are. Notice though that some of the stars seem to be in a line. We're going to talk about that. This one seemed to be the oddball of the group. Hold that thought. Let's look at a different one. This is Cygnus the Swan. Draw some lines so you can believe me. There you go. The famous summer constellation. And again, spinning it around, it does not look like what it was, does it? These stars are at all different distances from us in three-dimensional space. Oh, look, now here's Leo the Lion, one of the few constellations that looks like what it's supposed to be. See the lion, obviously, all right? But now again, we're going to change our perspective. Look how very different it looks. Here comes famous Orion. That's a shape many of you are familiar with. And again, look how foreign it looks when you change your position. Let's talk about why this happens. This handy little chart is a distance map of the most famous, the most bright stars in the Orion constellation. We have here the two-dimensional representation, as we may believe it to appear here on Earth, famous red Betelgeuse there. But then we have a three-dimensional representation here. Notice some of the stars are quite close. Bellatrix, well, close is a matter of opinion. 252 light years away, makes the shoulder there. But then Betelgeuse, the other shoulder of Orion, is farther, around 5, maybe up to 600 light years away. There is some margin of error with Betelgeuse. It's difficult to measure its distance. Then we see the famous Orion's belt. These three stars, Alnitak, Alnilam, and Mintaka, they appear as a line to us on Earth, and yet, notice at least one of them is a significantly different distance. Alnilam there, in the middle, yet they appear lined up. Again, constellations are not real. They are a figment of your perspective. It's because of where you are. Now, if you were elsewhere in the universe, it would look different, like I just demonstrated. Let's spend a little more time talking about Orion. Oh, by the way, before I do that, look, the famous Orion Nebula, something we often associate with Orion. Beneath his belt, we say it's under his belt, but of course it is not. It's far, far behind his belt. Yeah, so as I was saying, let's look at Orion in a little more detail. Let's move around in the sky a little bit here. And there is the Orion constellation. And we're going to do that same thing. We're going to kind of shift our perspective a bit. Let me speed it up a little bit. There you go. Of course, you couldn't actually experience something like this in real life because your spaceship would have to be going significantly faster than the speed of light, wouldn't it? But again, look at the star there in what we thought was the middle of the belt. Is not. Are there any questions about this? Does it surprise any of you? This is the topic of our discussion tonight. We're going to talk about not only the three-dimensionality of the cosmos, but also the tools that we use to prove this. You know, for you to be able to generate a three-dimensional simulation like this, you need some data. And over the last 200 years, humans have gotten very good at mapping the universe, especially the local universe. We're going to talk about how we do that during this show. And again, I strongly encourage questions. By the end of this, hopefully you will understand a bit about the science of astrometry. Oh, perfect. Someone just asked, how do we measure these distances? Excellent. So that's a significant portion of the show tonight, talking about the different tools that we use. And those tools vary And they vary tremendously based on context. For example, a tool you might use to measure a planet in our own solar system will be an extremely different tool than one you would use to measure the distance to a distant galaxy, for example. Yeah. Before we get into that, let's talk about some history really quick. This is a charming old engraving, often known as the Flammarion engraving. People see this a lot and think it's extremely ancient. It's not. This was actually created in the late 19th century. And it got famous and it started being called the Flammarion engraving because it ended up on the cover of a popular meteorology book written by Camille Flammarion. Its original name was Empedocles Breaks Through the Crystal Spheres. And that crystal spheres concept is kind of important because people used to think that the universe was indeed a sort of dome or a hemisphere, often crystalline in nature, that you could not cross. But this brave fellow apparently figured out a way. He claimed to find the place where the heavens met the earth, and then he crawled through and he achieved enlightenment in this mystical realm beyond the sky dome. Of course, this is ridiculous. There is no three-dimensional sphere encompassing our planet. We are not trapped underneath it. And the stars are not little tiny holes inside of that sphere, or hemisphere. Some people thought instead of holes in the sphere or the dome that they might be little lamps, and ancient words used to describe the stars often involved the language that included lamps. Of course, stars are not lamps, but people thought that stars were tiny. And I would like to ask that very simple question. Why did people think that stars were tiny? You tell me. Why do we think stars are tiny? I'm watching the chat. Wait, come on, guys. Just pick up the pace. We have like 5 people in here or something? I think we have more than that. I hope we have. Why did these stars appear small, and why did people think they were small long ago? What do you think? Yes, because they're so far away. Very good. Stars are enormous objects, aren't they? There are stars that make our sun look tiny, and of course our sun makes Earth look tiny. Our sun is a small star, but there are smaller stars, but there are also much bigger ones. But all stars, except for the sun, appear as specks because they are so extremely far away. The ancients might be forgiven for assuming these things. They had no idea. They had no way of knowing that stars were like our sun, that they had no way of knowing that the sun was a star, and that these objects were indeed whole other places, entire other locations that were enormously huge, but again, also enormously far away. That being said, we often assume that all the people who lived until recently had incorrect assumptions rattling around in their head about the nature of the cosmos. But there was a famous Greek philosopher by the name of Hipparchus who broached the topic way back in the year 160 BC, the notion that perhaps the universe was bigger than we thought, perhaps the distances were greater than we imagined. And this wasn't just some idea that he came up with. He's often credited with creating trigonometry, and his mathematics helped to demonstrate distances within our solar system. And very quickly, he and others who followed his teachings realized, wow, these distances are far greater than we expected. Their measurements were all based on things in our solar system, like I said. They weren't considering the distance to the far-off stars. They may not have thought the stars were that much farther away. Many people assume the stars were similar distance to the planets. And they assume that because planets also look like stars, don't they? Tiny. In that case, because they actually are relatively small objects, and they are far away, but not nearly as far away as, again, the stars. So yeah, we named a famous satellite after Mr. Hipparchus, and we're going to talk about that in a few minutes. That's one of the tools that we use to figure out cosmic distances. So I have a lot to say about a lot of things tonight. Before I continue, any questions? Let's see. How does it seem so close to Earth but is really far away? Are you referring to stars or planets, things like that? You might think the Milky Way appears close, for example, but the Milky Way only appears so because you can't tell how far away it is. You think you can reach up and touch it. I've often heard people describe it that way, that they think if they're in the desert or out in the ocean that they could reach up and touch the Milky Way, but that's because you have no frame of reference. The human mind judges distance and size based on reference frames, and if there are no reference frames, it often makes mistakes. For example, the famous moon illusion. People think the moon looks bigger when it's on the horizon. They think it's being magnified by the atmosphere. That's a popular myth. It's true that the atmosphere can distort space bodies, But the primary reason the moon looks big when it's on the horizon is because you have something to compare it to. If you see a giant tree that you know is 100 feet tall, but it looks like that, you know that it's far away. Your brain subconsciously tells you that it's a big tree, but then the moon looks much bigger than it, so suddenly your brain's like, oh, that moon is enormous. But again, it's only because you have something to compare it to. Once the moon is straight up, you don't have much to compare the moon to. The stars don't provide much context. You can't really relate to the stars when it comes to their distance just by looking at them. We're often tempted to do that. You'll often see a star that's much brighter than another one, and you think, that star must be much closer. It could be. That can sometimes be true, but it's also often not true. Questions? Can stars be bigger than planets? Oh, of course. Essentially, all stars are bigger than most planets, with the exception of ultra-low mass red dwarfs, which can technically be, in some cases, perhaps, smaller than the largest of gas giants. But yeah, stars are always enormously larger. I suppose I should probably bring up a graphic to prove that to you. Hold that thought. So I used this picture last week, and I was showing people the different stars, and one of them is the sun. It's that little speck there, that little pixel. Understand that, for scale's sake, if Betelgeuse here were depicting our sun, then Earth would be a speck, smaller than Sirius. So even though our sun appears enormous compared to Earth, it is itself a relatively small star. Stars tend to be quite large. They're some of the larger single-body objects in the universe. Yeah. Okay, so back to 3D land for a second. Before we get into the tools of the trade and talk about how we figure out how far away things are, I'd like to go over some basic terminology, including distance units. This is something that people often take for granted. Again, they think they know how big the universe is, and they throw words around like light years, but they don't know what they mean. So let's go over some units of distance. Now, this is a kind of a little Easter egg. If anyone can identify what that image is on the lower left, you get some candy. I can't send you any candy, but if you were here, I'd throw some candy at you, I promise. So let's throw out some units of measure based on context. Let's start with everyday life. What kind of unit of measure do we tend to use for distance in everyday life? Someone tell me. I'm watching the chat. What's a good example of a unit of measure that we use every day for distance? Anybody? You must interact or I will freeze this show. I will just sit here staring at the chat. There we go. Miles. Oh, that's a good answer. Thank you. All right, so there, look at all those people chatting. Thank you. All right, so 1 mile is equivalent to 63,360 inches. Now, this may seem kind of random that I brought up inches within a cosmological context, but you're going to see why. There is a reason to bring up inches. Some of you might already know where I'm going with this. Okay, so miles. Useful in certain contexts, but certainly not all contexts. For example, in our own solar system. If you're talking about something that's very nearby, perhaps miles would be appropriate. Let me show you something here. This is kind of neat. This chart goes from the scales of very tiny to the scales of very big, and we're going to start with the very tiny here. So Earth-Moon system, I would argue that yes, miles are fully appropriate. You can use miles, and that's not wrong. For example, satellites are a few hundred miles up. The moon is 240,000 miles up. Again, miles. I've said in my last chat, you could drive to the moon if you had infinite food, water, air, traction on nothing, you know. So 240,000 miles, that's appropriate. Now, solar system context. You could still use miles when describing distances within the inner solar system, but the numbers start to get big. But you can still do it. Far away. How far are we from the sun in miles? Does anyone here know? How far are we from the sun in miles? Someone's doing kilometers. Sorry, guys. I wish we could do kilometers, but I get complaints on the other side when I do that. Oh! I didn't ask about AUs. I asked about the number of miles between Earth and Sun. Does anyone have that answer? A lot. 93 million miles. Very good. Let's go back to our chart and add that. And someone by the name of Ed did actually introduce the unit based on that distance. 1 AU, 1 astronomical unit, and this is a term I recommend you add to your personal vocabulary, is the average distance between Earth and Sun. And the reason it's an average is because Earth's orbit is an inclined eccentric ellipse. So sometimes we're a little closer, sometimes we're a little farther. The average distance between Earth and Sun is 1 AU, 1 astronomical unit, and that's 93 million miles. Feel free to ask any questions you might have about that. AUs are definitely appropriate for use within a star system. So I could easily measure the AUs between things. Let me zoom in a little bit here. Venus, 0.72 AUs from the Sun. Mercury, 0.39 AUs. Mars, 1.52 AUs. Asteroid belt, 3.2 AUs. You see, AUs are very manageable for the context, within the context of a solar system because the numbers are tiny, right? Very convenient. It was important not only for the sake of convenience to establish the AU, it was also important for larger measurements. We needed to be able to apply the measurements we made of the greater universe to the motions of bodies within our solar system. I'm going to explain that in a minute. But we had to figure out some of these distances with great accuracy so that our much larger measurements later could be at least something resembling accurate. It's much easier to measure things when they're close than when they're far away. So yeah, let's go back to our chart. What if I wanted to measure something, I don't know, in a different star system completely? Would that be outer solar system? We still got small numbers. Neptune, 30 AUs away. Uranus, 19. But then I go to a different star system, and now AUs become a problem. If I were to measure the distances to these stars, I would have to use a bigger unit to be reasonable. So what is that unit? I think some of you are about to say it. What's the next unit up in our little cosmic measurement box? Oh, look at that, light year. Someone got it. Now, to help you appreciate how far a light year is, consider the fact that 63,241 AUs would fit within it. That is that many units, 63,000 times the distance between Earth and Sun. Now, you might start to see why I included inches, because you'll notice, by a bizarre cosmic coincidence, the number of inches in a mile is kind of similar to the number of astronomical units in a light year. So if you ever want to try to imagine the distance to the nearest star, which by the way is 4.3 light years away, you'd need to figure out how many inches that was if you wanted to convert light years to miles. If you wanted to go just 1 light year in your imagination, you could think of standing on a road and remembering that every inch on that mile of road corresponds to the average distance between Earth and Sun. So it does help you wrap your head around a unit that is enormously huge. Light years are hard to fathom. They're about 6 trillion miles with a T, 6 trillion, and I can tell you right now that that number is meaningless. If I say 6 trillion, you really can't imagine it. You can't even imagine 6 million miles, really. I might as well say I could say 6 gajillion miles. But with this AU analogy, it helps a little bit, especially when you convert to inches and consider 1 mile. Now, let's say you did have a stretch of road that was I almost said 1 light year long, 1 mile long. There couldn't be any stars on it because, like I said, the nearest star is 4 times that distance, Alpha Centauri, 4.3 light years away. Let's do something silly really quick. We're going to get our calculator out, and we're going to drive 1 AU. Now we have a very exact number on the screen. Now we're going to drive 1 AU, or the distance to the Sun, at a blistering speed of 70 miles per hour, because legal. To divide that by 70, it's going to take you 1.3 million hours to drive to the Sun. Let's divide that by 24. It's going to take you 55,000 days to drive to the Sun. Let's divide that by 365. It's going to take you 152 years to drive 1 AU. Let's make that a little neat and tidy. 152, multiply that by 63,241, which is the number of AUs in a light year. And it would take you almost 10 million years to drive 1 light year at the speed of 70 miles per hour. And like I said, if you did do that, if you did drive for 10 million years at 70 miles per hour, you would not be able to visit a single star because, again, the closest system, Alpha Centauri, is 4 times that distance. Any questions about that? Let's see. Okay. Now, some of you might be aware of a more obscure unit of measure that's bigger than light years. Anyone here want to share that with me? I bet someone has it. Would it be useful to assign space term to sound years, since light speed is at speed at the speed of sound, like a jet aircraft? The numbers aren't that much better. Let's go silly for a second here. So let's bring up a calculator again. Now we're going to drive to the sun, or fly to the sun in a jet airplane. 9,956. Divide that by 700 miles per hour, so 10 times faster. Well, that's better. 133,000 hours. Divide that by 24. 5,533 days. 365. Oh, look, it would only take you 15 years to fly to the sun in a fast jet. Okay, fine. Now let's multiply that 15 years by 63,241. Oh, look, it would only take you about 1 million years to fly 1 light year in your super fast jet. And again, you would not be able to visit anything because there are no star systems within that short distance of 1 light year. So that was a good question. Thank you for bringing up the jet. Okay, final unit of measure for this chart. Can you think of one more? And it's less commonly discussed. It's more of a tool, but many of you have probably heard of it. Oh, I got it. Someone got it. Very good. Parsec. So 1 parsec is equal to 3.26 light years. Now, that may seem extremely random and arbitrary, and that's because there is no relationship between light years and parsecs. Parsecs are actually part of the astrometric toolkit. That's a term we're going to learn tonight, astrometry, which is the science of measurement, the measurement of the position of things, the vector of things, the velocity of things. And parsec is a unit of measure invented to help scientists establish distances. We're going to talk about that right about now. Before I do, are there any questions? That's funny. I thought I said it. So how far is the closest star? 4.3 light years away. Specifically, it's 4.2. It's a member of a trinary system. The Alpha Centauri system is actually 3 stars. And the nearest member to us is nicknamed Proxima Centauri, and that's about 4.2 light years away. So now we need to figure out how we figured out these distances. Let's start simple. Let's start with figuring out the distance to things in our own solar system. It shouldn't surprise you that the shorter the distance between you and a body, the better you can do with accuracy. It's possible to figure out the distance to things with great accuracy if they're not all that far away. For example, look at this. Radiant reflection astrometry, the most accurate form of astrometry. We're figuring out how far away something is, the speed of it, the direction it's heading, by literally beaming some sort of energy towards it, and then we measure the reflection. Now, what's going on in this video? Someone tell, or a picture. What's going on right now? What do we see in this image? By the way, this is a real picture. This is not science fiction. It kind of looks like science fiction. Anyone know what's going on in this picture? It involves something we talked about in a previous show a few weeks, or was it 2 weeks or last week? I can't remember, or 2 weeks ago. What's going on in this picture, guys? Someone tell me. Why are we shooting a laser at the, whatever that is? What's that bright thing in the sky? I hope you know what that is. Are we not saying anything? Are we not speaking? Are we not typing? Let's see here. I think we're on. I could tell you. A laser pointed at the clouds. Oh, the sun. No, not the sun. Not the sun. That's the moon. We're shooting a laser at the moon, and the laser is bouncing off of those retroreflectors that the astronauts left there when they landed back in the 60s and 70s. That's how we figured out exactly how far away the moon is and how quickly we're losing it. We can determine with extraordinary millimeter accuracy the distance to the moon just by shooting lasers at it. Now, this is how we figured out the moon is leaving, about 1.5 inches per year. Yeah, someone got it. Lasers pointing at the retroreflectors. That's right. Now, that's true. We can figure out how far away things are with radiant reflection, but we can do something even cooler than that. Check this out. So this is actually radar beaming radio waves into space and bouncing them off of objects and actually essentially taking a 3-dimensional image of them. This is an asteroid called 2014 JO25, and this was actually imaged with one of the Goldstone radar dishes in California. Now, this is worth bringing up, and there's a little tangent that's worth diving into briefly. Someone asked me about some big news that happened last week. Unfortunately, the Arecibo radio telescope has collapsed. Some of you may have heard that a few weeks ago, some of its support cables failed, and they decided that it was too dangerous to fix, and they were going to decommission the thing, and they were going to safely demolish it, but then essentially it did it for them and it fell apart. So if you haven't seen that video, the reason I'm bringing this up is because Arecibo was one of the few facilities on Earth that could do this kind of science, that could actually send signals up and then receive return of high enough fidelity to image like this. So check it out. If you didn't see this sad video. Let's see, I'm gonna let it run. Everything's fine, nothing to see here, nothing to worry about. And then all of a sudden, one of the other cables snapped, and 900 tons, 2 million pounds of material fell down. And that was the end of Arecibo. Sadly, the end of one of the world's few facilities that could do radiant astrometry. If you haven't seen this video, I guess this is your scoop. Here you go. You get to watch it. I hope to see a replacement for Arecibo be built one day, including perhaps on the moon. Although right now, short term, we might want to try to build some ground-based facilities. You may have heard that China has a larger radio telescope now called the FAST reflector, but it can only receive. It does not send signals. Here's some footage from the drone hovering over the cables, inspecting them, and you can actually watch as the cables fail here. Watch this. And here they go. Yep. Almost 2 million pounds of material falling down to the dish. If you're wondering why it's so heavy, it's cooling equipment. Arecibo had to cool the amplifiers to a very low temperature to reduce their noise floor. And when I say noise, I don't mean acoustic noise, I mean radio frequency noise. So all that cooling equipment is very heavy, and that's why that gondola, so to speak, that carriage was so massive. And as you can see, a lot of damage can be done when something that heavy comes crashing down. So there's our sad video of the day. Let's move back on to what we were talking about. So, the most accurate tool for determining distance is to actually beam something at the object, radio waves or laser light, receive a reflection, and you actually get a very, 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 very precise measurement. Of course, this method is limited because it only works with things that are close enough to receive a relatively quick and strong reflection. In the case of the moon, it takes about 1.5 seconds for the signal to come up and come back. In the case of this asteroid, it took a few seconds because it was a few million miles away. I find it very impressive that we can actually image something with radar that is millions of miles away. That's darn impressive. Yeah. Before I continue talking about the tools we use to figure out distances, are there any questions so far? Someone says Goldeneye. Yeah, it's true. So they shot Goldeneye, that final scene in Goldeneye, at Arecibo, although in the movie they claimed it was some kind of Russian communications station for controlling a doomsday satellite. Yeah, so that's a little different. And apparently James Bond broke it when he got revenge on his former partner there. And that's the real reason Arecibo collapsed. Not really. That joke's been floating all over the internet all week. I'm not being original by telling you that joke. So, how big is that meteor? This asteroid is, well, it's over 2 miles across. Yep. The bigger it is, the easier it is to image, of course. All right, now, let's go to the next method. And this is where we get into the interesting science a bit. If you want to figure out the distance to a nearby star, then we need to use a clever technique known as parallax. Now, parallax is not a word that is unique to astronomy. It deals with the fact that something will appear here or there, depending on where you are, where the object is. Something that's closer to you will appear to move more quickly as you move. Something that's farther away will appear to move more slowly. Notice what's going on in this video. I'm going to speed up time a little bit here. You can see that Earth is orbiting the sun. You can see that we're looking at a certain star in the sky, and then that star appears to move. notice that the star appears to move differently than the stars behind it. It seems to be moving faster. The reason that star is moving faster, or appearing to, is because it is closer. Now, this goes to this speaks to that unit we talked about, the parsec, which stands for a parallax of 1 arc second. So 1 parsec of distance entails an apparent motion of 1 arc second of a body. By the way, there are no stars that close, so no stars have a parallax of 1 or less. Now, there was a famous star that was actually measured using this method way back in the 1800s. Let me see if I have it handy here for you. If I don't find it quickly, I will. Oh yeah, here it is, 61 Cygni. A star called 61 Cygni was discovered to have an unusually high, what we call proper motion. Now, this is a modern image of this star system. It's actually a binary system. 61 Cygni was noticed in the early 1800s by a famous Italian astronomer named Piazzi to have what we call a high proper motion. The star appeared to move quickly in the sky. This inspired other astronomers to study it in great detail. They were intrigued by its fast motion, and we were able to figure out its distance by employing parallax astrometry. Now watch this. If you look at the clock on the bottom of the screen, this is only 8 years of time. In only 8 years, look how much these two stars have moved. This is such an obvious motion that it didn't require the most advanced equipment in the world to determine the displacement from year to year. This can be done with an off-the-shelf home telescope now. You could easily, and by the way, that's what this is. The telescope that was used to do this was not an advanced giant observatory telescope. You could actually collect data like this. So let me go to the last frame, 2020, and then the first. So look, 2012, 2020, it moves that much. So the fellow that discovered this, the parallax, was named Bessel, and he's Friedrich Bessel. He was German, and he figured out the distance to the star was about 11 light years. He was pretty close to being correct. It's 11.4 light years, and we named it after him as Bessel's star. But we still also call it 61 Cygni. Now, Bessel used a device known as a heliometer. Check this thing out. You might think that's an ordinary telescope, but it has an unusual tool attached to it. The heliometer is a very clever invention. It's essentially a split prism where you can move one of the two prisms to control the split with very high precision. It allows you to measure very fine changes in the size or the position of something. They're called heliometers because they use them to measure the size of the sun, so we can figure out how far we were from it, because the sun grows and shrinks throughout the course of the year, since Earth's orbit is not a circle, it's an ellipse. But heliometers, thanks to their precision, could also apparently perform parallax astrometry. So this is how we figured out the distance to that star. Questions about that? Let's see here. Okay. Let's go find that star, shall we? I'm going to put up a different screen real quick. All right. This is the sky. I'm going to pause this. Let's go find 61 Cygni. Oh, I went too far. Let's see. Let's do this. Oops. Turn the ground on. There's no grass right now. Let's go to 61 Cygni A, which is actually the one with the nickname. There you see Bessel's star. Now, I'm going to speed up time. Watch this. Let's go real quick. Now, as you can see, we've only moved forward in time a few years here, and it's already noticeably moving. Bessel's star has what we call a high proper motion. I'm only about 20, 30, 40, 50, 100, Very quick motion, proper motion. And that's what was revealed in that that animation I just showed you. Let's go back to that. Questions about that measurement technique. Astrometry has a big problem. When you're trying to view something from Earth's surface, you have to look through a lot of air. You're probably aware of this. And that can be an issue when you're dealing with precision, right? So we have to figure out a way to deal with this problem. Let me show you what I'm talking about here. This is the famous star Sirius. Sirius is the brightest star in the sky. If you were to magnify it greatly with a telescope, as we have done here, you would see that Sirius was not a perfect little point of light because the Earth's atmosphere is causing it to twinkle. Twinkling is the term we use popularly for atmospheric scintillation, and it is the bane of astronomy. It makes everything more difficult. It's difficult to get sharp images because of scintillation, and it's very hard to measure the actual position of a thing because, as you can see, the position of a thing seems to wobble and change thanks to the air itself bending light chaotically. Stars do not twinkle. If you've ever seen a star twinkle, they do it because of the air, because of the atmosphere. Twinkle, twinkle, that's funny. So how do we solve this? Now, I'm not going to tell you. I want you guys to participate. If we need to measure very precisely, and the atmosphere is preventing it, what do we need to do, guys? Think about that. What do we need to do? Anybody? The atmosphere is preventing us from making high quality. Oh, go to space. Very good. Exactly. So in the late 1980s, the European Space Agency launched this thing, a very important astrometric space telescope known as Hipparcos. Hipparcos is named after that Greek philosopher we talked about a few minutes ago. And Hipparcos was the first purpose-built astrometric satellite. And it performs astrometric readings by taking advantage of Earth's orbit around the sun. Hipparcos orbited the Earth, goes along for the ride, so to speak. The whole sky appears to shift, and Hipparcos had sufficient enough resolution to actually determine the distance to things. And it did so with about 200,000 stars. Watch this. I'm going to zoom in on some random location in the sky, okay? Some random spot. I'm not going to pick one. I'm just going to go randomly. And as you can see, the star names start popping up, and they start to have a familiar prefix. HIP, in this case, 5, what is that? 59592. If you ever see any star in a star chart with an HIP prefix, it's part of the Hipparcos catalog, and we know its distance with very high precision indeed. So what do we have here for distance? 1,614.64 light years. We can be precise 2 positions after the decimal. Let's go to a different one. Let's find, I don't know. Let's go to some famous star systems. Let's go. Oh, that's not bad. Let's see. Yeah, okay. Coma Berenices, the Northern Crown. Oh, look, more HIP stars. See that? Distance, 277 light years. Here's another one. Distance, what does it say, 146? So 146 light years. So the HIP, the Hipparcos satellite, gave us extremely accurate distance measurements. And not only distance, but also speed and vector measurements. And it helped us to start mapping the Milky Way galaxy. Hipparcos was a big deal, and we still use the data, and we still refine the data even to this day. So it continues to be relevant, even though the satellite was decommissioned in the early 1990s. So Hipparcos was a big deal. However, progress marches forward. As you know, we need to do better, and recently we did a lot better. Some of you might be aware of a different space telescope. This is Gaia, and this is a big deal. The Gaia Space Telescope was launched much more recently in 2013. It is an extremely advanced astrometric satellite, and it spins around in circles, is still out there doing its job, surveying the entire universe all the time. So it's scanning the entire sky. Here's a picture of it during its construction. You can see how big it is. This big platter, this big saucer thing, is a sunshade, so it needs to be in darkness all the time. And there's some gentlemen there who worked on it. You can tell how big it is from their example. Let me show you what its orbit is like. Here's an animation of it opening up. The satellite actually orbits Earth and the Sun at the L2 Lagrange point. So it has the same orbital period as Earth. Let me get my head out of the way there. This type of orbit is used when you need to be in shadow, for example, or close to the Earth so you can maintain communications. And it gets away from the dangerous radiation, or I shouldn't say dangerous, the disruptive radiation from Earth's communications. And that's why a lot of satellites actually end up in orbits like this. It will stay out there for years doing its work. It's recently returned its third batch of data. I'm going to talk a lot about what Gaia has done. Before I do talk about the star distances that it's determined with astonishing accuracy, let me show you its asteroid surveys. So Gaia, even though it was not specifically designed for asteroid surveys, has provided this very accurate map of asteroids in our own solar system. All those green lines are the orbital paths of asteroids. Gaia can provide enough resolution to and enough work time to map the positions of literally thousands of asteroids, including some that might threaten the Earth. So there is a sort of a safety benefit to its work. But this is not Gaia's claim to fame. Gaia is able to perform astonishingly high-resolution parallax astrometry because it has the highest resolution sensor ever placed into a spacecraft. This is about 1 billion pixels, so 1 gigapixel of resolution. Every one of these little rectangles is actually a charged coupled device, a CCD detector. And because there's so many pixels available, because its resolution is so high, it can actually determine the positions, the luminosities, the spectral class of multiple stars simultaneously. It gets a lot of work done very quickly. The mirror of Gaia is a little bit unusual. It is a rectangular mirror, and it's packed with lenses which actually distribute the light from the mirror, and there's actually two primary mirrors, to different sections of that sensor board I just showed you. It's very sophisticated optics. What's interesting is there's no round optics in it, because they're not trying to produce a very high quality image. They're just trying to get that point of light of a star to focus on a small enough number of pixels to be able to tell it apart from other stars, figure out where it is. And again, just like the other satellite, Hipparcos, this spacecraft Gaia orbits the Earth, orbits the Sun, and does its important work. Any questions about that? How big are the optics? Actually, I believe I have a picture. Someone asked me for a picture. Hold that thought. Let me see if I have it handy. If I do, I will show you. Yes, it is. I do. So there is someone working on the primary mirror. And that's how big it is. I don't know how many feet it is, but it gives you some idea. Notice it's curved. The whole assembly is quite large, and the light path is very complex. It goes back and forth inside the assembly, again, being distributed to the various sensors necessary to do the important work. Gaia is a big deal. It can provide very impressive resolution, enabling us to see different motion of stars, including motions we haven't talked about yet. For example, we have the parallax of the star caused by the Earth's orbit around the Sun. We have the proper motion of the star caused by the star's actual orbit within the Milky Way galaxy. This is a big one. It can detect the wobble caused by the gravity of a planet orbiting the star. And then it can actually detect all of those motions combined, providing clear enough data that we can actually extract any one of these data points, or provide a, in this case, squiggle diagram to demonstrate the, again, apparent path of the Sun and the star. Notice I say the apparent path of the Sun. Even while it's measuring the motions, the vectors of different stars, it's also helping us understand the vector of our own Sun. So Gaia doesn't just help us understand the positions of stars in our galaxy, it also helps to determine the position of our own solar system and its motion. So that's a big deal. Questions about that? How long will it last? Does it have to download the data, or is there onboard? So it does perform data compression. In fact, most of the data, that's a very good question. Since you are interested in that, let me bring up a picture really quick. This is the actual layout of the sensors. So it has these wavefront sensors that look for alignment errors. Right there, it can reject any data that it knows is caused by a phase misalignment. Essentially, the satellite is crooked a little bit. Of course, that data is also used to correct any crookedness in the satellite's orientation. It also is able to use these what we call sky mapper CCDs, which essentially see the stars before they get to the astrometric field CCDs and eliminates noise. For example, cosmic ray impacts. Cosmic rays will often create false positive discharges on sensors, and it will essentially waste data on this little smear of light that was not actually a star. So the cosmic rays, for example, can be filtered out before the data is wasted from the astrometric field CCDs. And by the way, these are the ones that do all the work. These are the very important ones, the workhorses. These ones have color filters. These are actually determined, these are designed partly to facilitate the measurement of stars that have very intense color temperatures, either very low color temperature or very high color temperature. They can also be used to help determine the color temperature of a star in general, which gives you its surface temperature. And then this big one, this is important, radial velocity spectrometer. This allows us to detect redshift and blue shift. Redshift if a star is moving away from us, blue shift if it's moving towards us, and that's how they detect the wobble that might be created by an exoplanet, like we talked about. So when a planet orbits a star, it can actually cause the star to wobble. It cannot see the motion, but we can detect the wavelengths of light being compressed by closing or stretching from recession. So yes, it can do all these things, and much of the data compression, as someone asked about, is done on board before it's sent to the Earth, so it saves on bandwidth. And bandwidth is a big deal when space telescopes, because it's so low, because you're beaming signals over a great distance. Yeah. Now, these are good questions. I'm going to show you some impressive data. This is what Gaia sees. This is extremely exaggerated so you can understand it, but we're gonna move essentially our perspective around in three-dimensional space. Notice the stars seem to be dancing. Again, this is highly exaggerated so you can understand the concept, but this is what Gaia is always seeing, the entire star field shifting. Of course, the closer stars are moving faster or appearing to, the farther ones are not. Now, here's our constellation lines to help you understand what you're looking at. Notice some of them deform a bit. Oops, sorry. Bring that back up. Now we're going to move up, now we're going to speed up time, and we're going to see them distort. One of the most important things Gaia does for space astronomers, for scientists, it allows us not only to see where things are and how they're moving, it also enables us to figure out where they're going to be and where they used to be. Gaia's data is so strong that it allows us to build very accurate models of the universe. When it comes to astronomy, it's all about models. It's all about being able to predict the future or view the past, because things in the universe take so long to play out that we don't always have the luxury of being able to see them happen in a single human lifespan. Let me show you some of the stuff that we've been able to do because of Gaia. We have discovered that there is a S-like curve to our Milky Way galaxy. We've been able to chart that curve with very high precision. It seems to indicate that there was some sort of large interaction with a particular dwarf galaxy hundreds of millions of years ago. Now, this is quite neat. I'm going to pause this really quick. Let me get my head out of the way. This animation is simulating about 200 million years of cosmological evolution. We're talking about a very specific type of star, Cepheid variable stars, which are known to vary in luminosity at a frequency that's attached to their brightness. Cepheids are very interesting to astronomers because they allow us to figure out how far away things are. And we have run simulations trying to figure out how many of them have been born in the galaxy in our field of view over the last several hundred million years. So we're going to run a simulation, and then we're going to compare it to the actual data. And I want you to see how favorably they agree with each other. See all those stars being born? Again, this is a simulation. Keep watching. Now look at that. Notice that the simulation is very close to the actual presently observed Milky Way Cepheid variable stars. So it looks like we're onto something, doesn't it? This clearly works, doesn't it? Very impressive technology. Again, it's not so much just about measuring where things are and where they're going, but it's also about predicting where they were and where they're going to be. Very helpful when it comes to understanding how our galaxy works. Any questions about that? So I think that's quite impressive. Now I talked a little bit about Cepheid variables. And it's funny, it's a good segue actually, because they're the next tool in our toolbox when it comes to figuring out how far away things are. So far we've talked about direct radiation reflection, where you send a signal out to something and you measure the back reflection, figuring out how far away it is. We've just talked about parallax astrometry, where we can actually see stars wobbling to and fro because of the motion of our own planet around the sun. So now let's talk about Cepheid variables. Cepheid variables are they were famously used to help determine the distance to the Andromeda Galaxy. Edwin Hubble famously proved that the Andromeda Galaxy was a whole separate galaxy thanks to these stars. This particular Cepheid is known as V2, and it's in Andromeda, so another galaxy. And as you can see, its brightness changes. And it has a period of 31.4 days. Cepheid variables have a sort of light valve that essentially involves the opacity of helium, and the amount of helium they have determines how much energy they will build up before they change and grow or shrink. They're always growing and shrinking, not just changing in luminosity. And it allows us to calculate their exact brightness. So if you know how bright something truly is, you can figure out exactly how far away it is by measuring how bright it appears. So Cepheid variables are very important stars when it comes to astrometry, because it's like what we call a standard candle. We know its brightness, and that enables us to figure out how far away it is. Now, astronomers are never satisfied to have a single metric. They like to be able to compare data. So it's very impressive when you can use different techniques to measure distance and they agree with each other. In the case of Andromeda Galaxy, Edwin Hubble compared this data to data from a Type 1a supernova that had occurred in Andromeda a few years prior, another type of standard candle, and the distances seem to agree with each other. By the way, that distance is 2.5 million light years. It's incredible to note in this context, when we're talking about how big the universe is, how far away things are, that 100 years ago, we thought that the entire universe was the Milky Way. It wasn't until the 1920s that we figured out, wait, a lot of the things that we're observing in the cosmos are actually other galaxies. And Cepheid variables contributed to that. This is something amazing. I want to show you one of the most famous Cepheid variables in our own galaxy. This is RS Puppis. This is real. What you are seeing here are light echoes, separated by days of time. The period of this particular Cepheid is around 40 days, and what you are literally seeing is light from its surges, its peaks, echoing through the nebula that surrounds it. Because the nebular material, that huge cloud of hydrogen, is so far away from the star that it takes a few days for the light to reach it, and we're witnessing it. So what you literally are seeing here are light echoes being created by this variable star, RS Puppis. Any questions about that? Someone asked about dead pixels on sensors. Yeah, so cosmic rays very often destroy sensors, especially in outer space. There's very little protection. Also, sunlight, and also just being on all the time. Sensors fail over time, especially CCD sensors. And so just by using them, they will develop bad pixels. By the way, that's another form of data compression. When a spacecraft does develop bad pixels, that data will often be removed from the file so that the files are smaller, and again, saves on bandwidth. Yeah. So a Cepheid variable star is a star that varies in size and luminosity, and it does so in a very predictable manner that directly relates to its overall brightness. There are many variable stars, but not all variable stars are useful for astrometry, because not all variable stars behave as standard candles. That's a good question. Okay, so we have just now talked about all of the best methods used for determining distance to things within your own galaxy. And in the case of Cepheids, nearby galaxies too. The next method gets a little more difficult, a little more sloppy, a little less precise. I don't have any charts to show you about it. I can just tell you about it. It involves overall luminosity. We can figure out how bright something, quote, should be. We can then measure its apparent brightness and figure out what we think its distance is. But without tools like Cepheid variables, those guesstimations will not be as accurate. And so there's a big leap now. So we're going from a few hundred or a few thousand light years of distance and measurement to millions, tens of millions, hundreds of millions of light years. It's not until you get up into a very incredible distance of 5 billion light years, give or take, that you can start to use another method called redshift astrometry. Some of you have probably heard of redshift, or blue shift. I've already mentioned it. As the universe expands, and yes, the universe is expanding, galaxy clusters move away from other galaxy clusters, and this actually causes their light to shift towards the red, or if they're speeding towards us, shift towards the blue. Andromeda Galaxy is famously blue shifted because it's actually speeding towards the Milky Way. But most galaxies are speeding away from us. So what you're seeing here are the spectra of a bunch of random galaxies, and they're being overlaid on the same image, and you'll notice they disagree with each other. These two, let me see here. These two are very good. They're very much in agreement with each other. So they're probably almost the exact same distance from us. But some of the others are offset. This one's clearly a little bit redshifted, even though they're in the same part of the sky. So this one here is farther away than the one below it. I want to show you something really quite neat. This is the Hubble Deep Field, which you've probably heard of. Let me put it on the screen really quick. Just give me 1 second. Now, the Hubble Deep Field is one of the most impressive images ever taken. This is actually the Hubble Ultra Deep Field. The Hubble Space Telescope focused on a very tiny patch of sky for literally weeks, and it generated this image of extraordinarily distant galaxies. Now, the reason I wanted to bring this up is because some of the galaxies in this image are so far away that they are visibly redshifted. So you don't have to use a diffraction grating or a spectroscope or a spectrograph like I did in that last image. You can actually tell they're redshifted just by looking at them. So watch. I'm going to move my mouse around here. This really blue galaxy is only 2.7 billion light years away, but then let's look at these red ones here. That red one is 10.4 billion light years away, 10.5 billion, 11.1 billion, very far. This red one here, look at this, 10.7 billion. But then let's look at another one close up. Oh, only 8.3, that's actually quite far. Let's see, here's a nice close one, 5.7 billion. I find it remarkable that the light of these galaxies is so severely redshifted by cosmic expansion that you can tell that they look red just by looking at the picture without using special instruments. Look at this one, 9 billion light years away, 9.5 billion light years away. I'm going to move my head out of the way really quick because I found one that was quite impressive. Oh yeah, look at this. See this tiny little red dot? Watch this. 10.1. Oh wait, let me see if I'm over here. 8.3. Oh, look at that. There it is. 13.1 billion light years away. That is the most distant one I found on this image. I cannot really describe to you how far away that is. That is so far away that we are essentially observing an object on the very edge of the observable universe. The universe is only a little bit older than this galaxy. So we are seeing this galaxy as it appeared not long after its birth, after the Big Bang. And when we study its spectra, we find that it's extremely low in metallicity. It's very poor in heavy elements because when the universe was extremely ancient, it didn't have lots of heavy elements. So when we compare the light of this galaxy, that tiny little speck, to a more modern galaxy, we find that it's metal poor, where young galaxies, or rather, I should say, our perspective of a young galaxy, like with our own galaxy, the Milky Way, appears younger because they have more heavy elements, and these ancient ones have less. But again, the redshift is so extreme here that we actually see a red dot. The galaxy looks red because its light has been stretched by cosmic expansion. Questions about that? I think that's pretty darn amazing. So we figured this distance out with redshift astrometry. It tends to be good for extreme distances. This is a tool you use when you're looking at other galaxies or quasars, which are very active galaxies that contain black holes that are feeding on their core regions. So many of these are quasars, actually, not just regular galaxies. So we just talked about different tools, and this particular example Redshift astrometry is the tool we use to figure out distance to the most extremely far away things there are. Any questions about that? That's right, the Hubble Ultra Deep Field. Is there an area that doesn't have the wave moving through it? I'm not sure what you mean by that. Let's see. All right. I don't have much more material. I do have some cool videos to show you just as we start to wrap it up, but I really would love to hear some more questions from you guys before I do wrap it up. So feel free. Let me show you something about Gaia here really quick. This is how it scans the sky. It's up there spinning around, constantly observing the entire universe, and it builds this three-dimensional model. Now watch this. We're going to spread this out. See that? There have so far been 3 data dumps. In 2016, we received our first release of data from Gaia. As you can see, the data is not quite complete. And then 2018, the second data drop. Notice there's like little stripes where it's not completely finished. But now, recently, we have got the last data drop, the most recent one. So this is from literally a few days ago. It was good timing. I didn't plan that, by the way. But just a few days ago, this dropped. This is an amazing image because it's not actually a picture. It looks like a photograph. It looks like just a picture of the Milky Way. But watch this. When I zoom in here, every one of these dots, that is a mapped star. So that is not just a picture of the universe. That is a star with a known distance. This is actually a map generated by Gaia with over 1 billion stars in it. We have determined the distance to over 1 billion stars, thanks to this space telescope. Look, we have some famous things over here. What's this? Those are the Magellanic Clouds, 2 dwarf galaxies that orbit our own Milky Way, and they're close enough that Gaia was actually able to measure them. They're about 165,000 light years across. Amazing. Questions about that? Yeah, so we have a great conjunction of Jupiter and Saturn coming up. That's a good astrometric example because they're close enough you can measure them in a much more old-fashioned method. We're going to do a whole show about them next week. So we're going to talk about the great conjunction of Jupiter and Saturn next week. Let's see if I have anything left to show. I do have some things left to show you, but guys, I'd like to start going through the questions now. I had a lot to cover, so I didn't spend as much time in the chat this time, but I'm going to read them now. Feel free to think of questions while I'm doing that. I think we'll wrap it up in about 8 minutes. So let's see. How can you tell the difference with stars and planets? Well, in a telescope, a planet will look like a planet. It will be, if it's close in our own solar system, that is. Of course, planets give off no light, so they're very difficult to study in other star systems. And by the way, those are exoplanets. And we can see exoplanets if they block the light of their parent star. We can see them if they wobble their parent star. We talked about that a little bit with this particular space telescope. But when it comes to with the naked eye, without a telescope, you can often tell a planet from a star because the planets shouldn't be there. It's out of place. Planets seem to move around independent of the fixed stars. And so they will appear in different places from night to night. So that's a good question. Why is a star not a planet? Stars are stars because they can undergo thermonuclear fusion. Planets do not, and that is the defining characteristic of a star, the ability to fuse hydrogen into helium at a minimum. Let's see. How far is the closest star? Are we losing the moon? Yes, we are losing the moon. Will we build another moon? I don't think that was about the moon. Yeah, so it was about the telescope. Maybe. Let's see. Let's see. I'm still reading your questions. Feel free to write more. Oh, that's a good question. What is used as the fixed known reference to determine distance by parallax? You can change the reference frame depending on the survey you're doing. It tends to be the sun. By the way, speaking of that, I wanted to add, thanks to this new data, we have further refined our understanding of the sun's position in the galaxy. The sun is about 25,000 light years from the core region, and it's orbiting at a speed of about 500,000 miles per hour. So the sun is moving at 500,000 miles per hour, and it's orbiting at a distance of roughly 25,000 light years from the core region. Good question. Does it have to download the data? How many videos of the space station appear to be dead pixels? Different colors. The different colors signify the different surface temperatures of stars. Blue is hot, and red are the coolest. So the red stars are the coolest and blues are the hottest. All right, we're going to do something fun in the last few minutes. I want you guys to list for me your favorite constellations, and I'm going to show you how they change over time. So someone, give me an example of a constellation that you like, and I will show you what it looks like over time. Orion. We already did Orion. That was a pretty good one, actually. We have some nice data from that. Let's do a different one. I'm a big fan of Orion myself, but let's do a different one. Someone else said Orion. Okay, Andromeda. All right. So let's go find the Andromeda constellation, not the galaxy. Now, right now we're on Earth. I'm going to go to the Sun. And no, there's no grass on the Sun. That is a glitch. Okay, now that we're viewing the universe from the Sun, let me get my head out of the way. And I'm going to speed up time. Now watch this. Notice that the constellation is changing shape. Notice other stars are moving around. Let's zoom in a little bit here. Let's go a little faster. Look at all the stars moving. Now, we stop moving because it is now the year 99999. This is the year 100,000, and Andromeda looks different. Let's go back in time. Now it's the year negative 99999, so 100,000 BC, or give or take. And as you can see, it moved a different way. Let's go back to now. Moving time a little faster here. Watch. Come on now, speed up. Now we're back in the future. Now let's go back to now. Andromeda is kind of a boring one, but it didn't look that exciting. Oh, Taurus is a good one. Watch this. Let's go to Taurus. Oops, if I could spell. All right, here's Taurus. Now Taurus is actually a star cluster. And these stars are going to move very dynamically indeed. Watch. See that? Now the head of the bull is all deformed. Aldebaran has moved quite a bit. And the reason Aldebaran moves so much is Aldebaran is only 36 light years away. So it appears to move quickly as a result. Let's go back to now. Let's go back in time. See that? Let's go back to now. It deformed. That's a good one. Let's see. Someone's got Scorpio. Now, Scorpio was a good one because some of its stars are very far away and some of them are close. So let's go to Scorpio. Let's lock on to a star in Scorpio. Let's lock on to Sargass. There's a reason I'm locking onto that one. Speeding up time. Notice Sargass isn't moving that much, but this star moved a whole bunch. HIP 84143. Look at that. Distance of only 73 light years. So that star appeared to move quite a bit, didn't it? Let's go back in time now. Again, now we're in the year negative 100,000. This star over here, one of the stars in Pavo, it moved a lot, didn't it? This distance is only 20 light years, 19.2. Not surprising, the close stars appear to move quite a bit because of perspective, right? Guys, it's possible to do these simulations because of all the data we've collected from amazing astrometric instruments like Gaia and also Hipparcos before it. Let's do one more. Cygnus, okay. Now Cygnus has some far stars. Deneb here, very far away, 1,400 light years, but then Albireo, well, that's 400 light years away, ain't so close. Let's see, and then Saturn here. That one's very far away indeed. 1,832 light years. Let's lock on to Saturn, and we're going to speed up time again. Interesting. This star moved a lot. because it's close, 72 light years, but the rest didn't move very much, did they? Because they're so far away. Let's go back in time. Now we're in the past. Let's go into the future. Future. Let's go back to now. Everything changes because of our motion, the sun's motion, the motion of these stars. That means that the sky changes all the time, doesn't it? Questions about that? That's a good one. All right, so I promised to start to wrap it up. I'm going to show you a video. This might impress you. We've talked a bit about astrometry in our own galaxy. Now I'd like to show you something from the Sloan Digital Sky Survey, a 3D sky atlas that is, in this case, based mostly on galaxies. We're not only limited to the ability to map our own galaxy now, we can actually figure out the distribution of galaxies in galaxy clusters. So let me show you what I'm talking about. So this is a simulation, of course. We're not actually flying through intergalactic space, but the positions of all these galaxies are known. As you can see, galaxies are all tilted every which way, up and down, left, right. There is no up in space. And as you can clearly see, galaxies do cluster, don't they? The distances between these are really hard to fathom. We're talking about tens of millions of light years at least between most of these groups. Many of them are hundreds of millions of light years across. This entire field is several billion light years across in this simulation. So the universe is understood to be three-dimensional beyond just what we can measure directly in our own galaxy. That's fairly awe-inspiring and maybe even a little frightening. It is hard to wrap your head around just how vast the cosmos is. All right, questions. Do nebula move? Of course, all things move in a galaxy. Everything's always moving. It's really hard to actually see, it's really hard to define the word stationary because anything's moving in relation to something else. In fact, motion implies relative motion. It implies that you've chosen a specific vantage point and are observing something moving in a way that is different than you. By the way, because of that, if you are living in, let's say, a star system and it moves at a very similar speed and vector of another, then between the two of you, you wouldn't see very much motion, even though you're moving at hundreds of thousands of miles per hour in relation to the core region of your galaxy. When it comes to position and speed, you have to assign a reference frame or it's all meaningless. Good question. How far away is Polaris? How much has it moved over time? Well, Polaris is actually one of the stars we've measured with great accuracy. I suppose we could wrap it up with that. Let's see. Hold that thought. Let's go to the North Star, good old Polaris. As you can see, its distance, I was going to say it, but I didn't want to be wrong. Its distance is about 432 light years. And let's lock onto it and speed up time. As you can see, it moves. But at a distance of 1,000 light years, it moves fairly slow compared to some of those other stars. See that? By the way, that's not the reason we lose the North Star. We don't always have a North Star, but that's not primarily because of Polaris's motion. It's because of Earth's axis wobbling. We're going to talk about that in one of our shows coming up, actually. All right, it's your last chance to say something. Last chance to do something. Thanks for coming, guys. Let's see. Last chance. I hope we learned a little bit about the three-dimensional universe. Hope we have a better understanding of our place in it all. And I was really hoping for you guys to understand how far we've come when it comes to understanding distances, speeds, directions. And I think I've thought of my final thought. So all this stuff is moving around, and I haven't told you which way the sun is going. So if you find the constellation of Hercules, right about where my mouse is the direction our sun is going through the universe, or through the galaxy anyway. You wouldn't know it to look at the sky because it has no relation to the celestial equator or the galactic equator or the plane of the ecliptic. But our solar system is heading in roughly that direction right there. I think that's interesting. If you wish to leave the solar system, it would behoove you to go that way because you would be maximizing your velocity because you'd be taking advantage of the speed of the sun. You inherit all that speed when you leave. When you leave Earth, you're still going the speed the Earth was going. You're just adding a little bit to it with your rocket engines. So yeah, if you wanted to leave the galaxy, your best shot would be to go in that direction because you'd be inheriting the speed of our solar system. However, we're only going 500,000 miles per hour, and the escape velocity at this radius is about 1.2 million miles per hour. So you're not going even half fast enough to get out of the Milky Way galaxy. It's important to remember that the Voyager probes and the New Horizons spacecraft, they will never leave the Milky Way. They will continue to orbit the core region along with all these other stars because they're not going nearly fast enough to escape the Milky Way galaxy. And that's the kind of stuff that we can know thanks to the science of astrometry. All right. Well, this has been fun. This is a fun topic. How long would it take an unladen sparrow to fly? That's funny. Monty Python jokes are always welcome. So I am going to be signing off. I hope this was worth your time. Next week, we're going to be talking about another form of three-dimensional universality with the great conjunction of Jupiter and Saturn, which is another example of a figment of perspective. Well, with that, stay curious. If you had fun, please like and subscribe. And I will see you next week.